So I'm going to talk about neurophysiological correlates of dual tasking in people with Parkinson's, and specifically in freezing and gait, people with Parkinson's with and without freezing and gait. This work was accepted last week in experimental brain research, so hopefully you'll see it in the next few weeks. And it's a joint work with myself and Conor Fearon, who's a neurologist on it. It's a study I quite like. So we're going to investigate the impact of walking on a simple behavioral task in people with Parkinson's with and without freezing and gait. So I'm going to use FOG plus for with freezing and gait and FOG minus for without. And then I have some controls as well. Then we're going to use mobile brain imaging, EEG while walking, to investigate how walking impacts the motor processing, decision making, and the automatic processing. And it seems weird because actually I should say automatic processing then motor and decision, but I'm going to present to you how we kind of came to this. So first thing, Parkinson's disease. Well, thankfully the other two speakers have done a nice summary for me, but Parkinson's disease is neurodegenerative, characterized by loss of dopaminergic signals in the basal ganglia. The symptoms that I'm most interested in are tremor, bradykinesis, postural disturbance, and specifically freezing and gait. There are many non-motor symptoms, which impulse control, as Ignacio just talked about. And the treatments really treat the symptoms. And so it's dopamine replacement or deep brain stimulation. But freezing and gait, it's an intermittent gait disturbance where someone's feet get frozen to the ground. Most apparent in late stage Parkinson's, and it affects 60% of patients with Parkinson's at different stages. But the reason why it's very upsetting about the freezing, but it causes falls. With or without Parkinson's, falls are the leading cause of reduction in quality of life and life expectancy in people over 65. The issue with Parkinson's and freezing and gait specifically is it's very poorly understood. There's no effective treatment. It's difficult to understand, and it's heterogeneous. So, our experiment. It's a very simple experiment. It's just a target. So you see a plus, then you see an X, and you press a button. And they're random. So 80% of the time, there's a standard, which is the plus. 20% of the time, there's a cross, which is target, and that's when the person responds. There was a correlator that was part of another study, but they're just focusing on the thing in the middle. So we had three groups. People with Parkinson's with freezing and gait, people with Parkinson's without freezing and gait, and young controls. They did two conditions of that task. One when they're sitting and one when they're stepping in place. Now, I'm going to later on just use the word walking, but stepping in place for safety reasons. They're just stepping left, right, left, right. And while they're doing that, we're recording EEG. I put in one of the earlier EEG studies I did with the Fox Lab, looking at EEG while walking. And we convert the data to the current source density. So EEG while walking, mobile EEG. That's it. So here we have our little EEG cap. And in this example here, which is from my time in Albert Einstein College of Medicine, they're walking on a treadmill. So why EEG? EEG is great. It's system level snapshot. It can be used to look at attention deployment. It has temporal resolution, is what we care about. It's lightweight. So in theory, you could walk around the world with an EEG cap on, and people do for clinical reasons. And also you could do fancy online looping. So to our results. So first, let's talk about the sitting. So on the left side of the graph, we have our freezing group, FOG plus. And so the individual, that's individuals, and the dark is the group. And so what we have is the freezing group, and the middle group is the not freezing Parkinson group, have similar response times. And the younger control group are faster. Nothing really surprising there, but it's nice that there's consistency within the people with Parkinson's. What we see when they're stepping in place is something quite different. All of the people with Parkinson's with freezing and gait get slower. And maybe that's no surprise. You're going, oh, of course, you're doing two tasks. But in previous study with Brenda Malcolm and colleagues in Albert Einstein College of Medicine, we showed actually people sometimes will get faster at simple tasks while walking. And this was the case for people without freezing and gait. and controls. So they actually got faster at the task while doing two things because it's a simple enough task to do. So this is nice behavioral results because you have this interaction between the two groups. But the question is, what's happening that's causing this difference? So firstly, our EEG results, we have a standard evoked response, and I'm looking over the central parietal region. So that's our standard evoked response, which is the plus, and then the target, which is the one they're clicking to, is the red. And what I have here is the dotted line is when they responded. So that's a response time. Now, one thing we can take away here is that both the standard and target are relatively similar prior to around 200 milliseconds. And if we subtract them from each other, what we see here is what's classically called the P3 response, or the central parietal positivity. So that's for the controls. Now, for the people with freezing and gait, exact same thing. What we see is a very clean P3 decision-making response, because this is our indirect measure of decision-making, or direct. Then with the people without freezing and gait, with people with Parkinson's, we see something very similar. And then we have our young controls. Now, looking just at the subtraction waves being, we don't care was the standard versus target, we care about the difference between them. What we see is CPPs, or P3s, for the freezing groups, and the control group a bit larger, but quite similar. Below that, we have their topo plots of the distribution of activity across the scalp. And what we see is a central parietal positivity, which is commonly seen as P3. But we also note that in the people with freezing and gait, there's something happening in the frontal area. So we investigated that. Now, that frontal area is motor, not frontal as in decision making, but motor response. And we've found for each individual something called a lateralized readiness potential, where you subtract the motor potential for the left and right hand from each other to see inhibition versus excitation. Now, for a simple single button task, there shouldn't be a very large motor response. But for the freezing of gait group, there was. So that's very interesting. So this is still just sitting, but their response time was the same as the non-freezing Parkinson group, but they still are recruiting more area. So what about stepping in place? So here we are. We have our standard and target, and then we have our subtraction wave, and we have a P3. Similarly, for the non-freezers, very nice, and for the control group. And I was delighted to see this as well, because doing moving EEG, there's a concern about noise, but I didn't do anything overly fancy with the data. I just kept classical analysis because I wanted to show you don't have to do anything too fancy to get nice looking data. And what we see here is similar looking P3s from 400 to 600 milliseconds and later. And the topos, not as clean, but still you see a nice central positivity. So that's very reassuring. But that's me looking at the relation. And now we look at motor once again, and we see once again, the freezing and gait group have a very large negative going motor potential between about 350 to when they have their button press, while the other two groups don't really need to recruit motor areas. So it's a larger and earlier onset of the lateralized readiness potential than when sitting. So therefore, they're recruiting more of their motor area. And therefore, we would argue that they have to recruit more resources to do something that's very simple. And that's why we believe there's a delay in the response, because they're already at their limit. And then you're asking them to step as well. But there was also another interesting finding for us, is that you see for the FOG minus group, so the middle graph, and the control group, the right-hand side, their sitting and stepping curves, their subtracting curves, track each other quite nicely. But for the freezing group, there's a separation early on. And we posit that the difference in the early evoked response suggests the loss or reallocation of early processes when dual tasking. And that would explain why there's a knock-on effect in response. It's not that we're seeing a difference in the decision-making, we're seeing a difference in their automatic processing and their motor. So in conclusion, the behavioral data showed that the people with Parkinson's with freezing and gait had slower response times when stepping compared with sitting, while it was the opposite for the people with Parkinson's without freezing and gait and the controls. They were faster when stepping. So therefore, they were getting benefit from doing activity, while it's the opposite for the freezers. Then using EEG, we're able to drill down and say, oh, it looks like it's a motor issue because the people with freezing and gait have to recruit more motor areas, but there's also an issue with response conflict, which touches a bit on Ignacio's as well. But we did not see a difference in the decision making. So the impact of locomotion on generating the N2 and lateralized readiness indirectly implies that these functions compete with the locomotor resources. So this is part of many ongoing studies that the highlighted people are involved with that, but all these other people have been involved in many of the other mobile brain imaging studies I've conducted over the years. And every year at the Albert Einstein College of Medicine, we would do an event for children with autism. And that's why I had access to a Cookie Monster outfit. I don't own one normally. So any questions?